All right, this is chapter 7, and we're going to talk about linear regression. Now, we laid a foundation of linear regression in chapter 6, so scatter plots and correlation. And what we want to do now is take it to the next step. So once we've shown that we have a strong or relatively strong linear association, we would like to be able to come up with an equation that represents that linear association. And that process is called linear regression. All right. So let's take a look at this example. This is the amount of protein for Burger King items and the amount of fat in there. As you can see, and if I was to describe this association, okay, we would have a probably a strong, okay, positive and roughly linear association between the amount of protein and the amount of fat in items on the Burger King menu. Now, if you notice here, they all follow a general pattern. So we would like to be able to come up with this equation of the line that fits this data. Okay. So the correlation for the previous example is 0.83. Using that value in the graph last chapter, we said there is a fairly strong linear positive association between protein and fat. In this chapter, we will say more about the linear relationship between two quantitative variables with a linear model. Key word here is model. So this will not give us not exact answers. We're only going to model the relationship. So the linear model is just an equation of a straight line through the data. The points in a scatter plot won't all line up, but a straight line can summarize the general pattern with only a couple parameters. So a linear model can help us understand how the values are associated. Now, models won't be perfect regardless of the line we draw. As George Box said, all models are wrong, but some models are useful. So our models will never give us an exact answer 100% of the time, but they will give us useful answers, okay? Some points will be above the line and some points will be below. The estimate made from a model is a predicted value, okay? And we will denote that with y hat, and that literally is how you pronounce that, y hat. So the difference between an observed value, this is the value from the data, and its associated predicted value is called the residual. To find residuals, we will always subtract the predicted value from the observed one. So we say the residual equals the observed minus the predicted, or y minus y hat. Y is the data value, and y hat is the predicted value from the equation. You'll see we will sometimes call this E for the residuals, y minus y hat. So what do these things mean? Well, a negative residual means the predicted value is too big, or it's also known as an overestimate. A positive residual means the predicted value is too small. It's an underestimate, okay? So these two common sense will come up on the classwork activity pretty shortly. So let's take a look here. Here is the Burger King example with the amount of protein and the amount of fat. And here's our line. Now, if I take a look at an actual data value, it's right there. And if I plugged in the x into my equation, I would get a predicted value of y hat. The difference between these two values is a residual. Now, this residual turns out to be negative 11, which means I have an overestimate of what I should get. So some residuals are positive, others are negative, and on average, they're going to cancel each other out. That's why it's going to be a good model. So we can't access how well the line fits by adding up all the residuals. Remember, positives and negatives. So what we do with deviations was we squared all of those deviations. In this case, we're going to square all of the residuals, and then we're going to add the squares. So the line of best fit is also known as the least squares regression line, because what we actually do is we find the line that minimizes the squared distances of the residuals. Okay. So the figure shows the scatter plot for z-scores for fat and protein. If a burger has an average protein content, it should have about average fat content. So we would have a mean point. You know, this is standardized scores. So moving one standard deviation away from the mean in X moves our standard deviations away from mean in the Y. So this relationship is actually very important, and we may need to come back to this. If I tell you one variable has one standard deviation, you need to be able to calculate how much is going to result in the other variable change. Okay. So put generally, moving any number of standard deviations away from the mean in x moves us r times that number of standard deviations away in the mean in y. Okay. So r s of y over s of x is basically what we do. Okay. So we can reverse it also, right? And that's going to flip it this way. So there's a relationship between these variables. Okay. So how big can a predicted value get? R cannot be bigger than 1 in absolute value, so each predicted y tends to be closer to its mean in standard deviations than its corresponding x was. This property is called regression towards the mean, and this is also why we call this a regression line. So notice, what names do we call this? We call this thing the line of best fit, because it represents the data well, best fit. We call it the least squares regression line. And now we just call it a regression line. Okay. By the way, you may see this as LBF, generally not, but you will see this as LSRL, least squares regression line. All right. So in algebra class, when we wrote the slope-intercept form of line, we had y equals mx plus b. In statistics, we write this slightly backwards. We will put the y-intercept first, and we will call that b sub 0, and we will put the slope second, and we will call that b sub 1. We always write y hat whenever we're finding a regression line to emphasize that these are just predicted values, not actual values. The model says that our predictions from the model will follow a straight line. If the model is good, the data values will scatter closely around it. So we write B1 and BO for the slope and intercept of the line. B1 is the slope, which tells us how rapidly y hat changes with respect to x. And B0 is the y-intercept, which tells us where the line crosses the y-axis. So another formula we have here for B1 is this. B1 is equal to r times s of y over s of x. So if I'm able to calculate the standard deviation of y and the standard deviation of x, and I can calculate the correlation coefficient, I can now, by hand, calculate the slope of the regression line. Our slope is always in units of y per x. Okay. Now for our intercept, we can find the intercept by taking the average of the y's minus b1 times the average of the x's. Okay. Now look at the order here. You have to calculate the slope first by hand, then you can calculate the y-intercept by hand. Now, good news is we will almost always use technology to find the equation of a regression line. Your calculator has a linear regression tool, and computer software makes a table for regression. This table is what is usually provided on the AP exam. So we will have technology, we will use your calculator, and tables will be provided on the AP exam. So we really don't have to do a lot of these things by hand. Now, on a computer output, this is what's given to us when we do a least squares regression line. So you will always be given r squared. Remember, r squared is simply going to be related to r by squaring it. Therefore, going backwards, r is simply the square root of r squared. So this number is given to you, you can calculate r. This is called the standard deviation of the residuals, and we will deal with this a little bit later. Okay. And then basically what you really just need is this column here. The intercept is your B0 and the protein and B1. That's going to be the slope of your value. All of this stuff comes up later in the course, but that's basically all we need to read from this table. So the regression line for the Burger King data fits the data well. The equation is fat hat equals 6.8 plus 0.97 protein. So this is also known as y hat equals 6.8 plus 0.97 times x. Notice this was BO and this was B1. Okay. Now, if I want to make a predicted amount, all I do is I take the amount we want to predict and we substitute it in for the x variable, solve it, and we get a prediction, y hat. All right, so since regression and correlation are closely related, we need to check the same conditions for regressions as we did for correlations. We only can do a regression for quantitative variables, only if the data is straight enough, and only if there are no outliers. So here's example 1. A study examined the relationship between the fuel economy, miles per gallon, and horsepower for 15 models of cars produced. The regression model, MPG hat equals 46.87 minus 0.084 HP. So if the car you are thinking of buying has a 200 horsepower engine, what does this model suggest your gas mileage would be? So all we need to do is plug it into the equation. MPG hat equals 46.87 minus 0.084 times 200. When I calculate that, I get a prediction of 0.84. Now what we like to do is write this in a text. So I'm going to put that here. Okay, so that text might look something like this. The model suggests, let me make this a little bit bigger. Okay. Suggests that cars lose an average of 0.84 miles, MPG, miles per gallon, per every, oh, that is not what it says. I think we're actually, I'm a little bit off. All right, this is incorrect. Okay, so let's just go back here. I made a wrong calculation. This is the right, but I got the wrong calculation. Okay, and it should have given us 30.07 miles per gallon. And that's it, that's all you do. Okay. Example 2. So example 1 describes a regression model that uses a car's horsepower to estimate its fuel economy. In this context, what does it mean to say that a certain car has a positive residual? So now let's go ahead and write what that means. Okay. So a positive residual would mean the car gets better gas mileage than the model predicts for a car with that much horsepower. Okay, so notice the model only predicts. Model only predicts. So in example 3, here we go. In example 1, the regression model relates horsepower to the fuel economy. Explain what the slope means. So the slope is negative 0.084. Now this number might not look good. So this, remember, slope is over 1. What if I multiply the top and bottom by 10? I would get negative 0.84 over 10. So watch how I do this explanation. The model suggests that cars lose on average, or an average, of 0.84 miles per gallon per every additional 10 horsepower. Okay, so it just makes this number a little bit better. So notice here in my description, the lose, that's where I got the negative when I'm interpreting. Okay, I used the actual number for my slope, but I changed the units so it made a little bit more sense. We usually don't have 1 horsepower in cars. So I made it 10 to make it a little bit better. You could have made it 100, but that's probably too big. So the units just need to make a little bit of common sense. All right, example 4. The correlation between a car's horsepower and its fuel economy, miles per gallon, is R equals negative 0.869. What fraction of the variability in fuel economy is accounted for by horsepower? So this concept here, we'll talk about this later, is called the coefficient of determination. So that is simply r squared. So all we have to do is take r, which was negative 0.869, and we're going to square both sides. So we get r squared equals 0.755. And we usually do r squared as a percentage. So we convert that to a percentage. Okay? So we might write a sentence that looks something like this. Okay? 75.5%, that's the fraction, of the variability in fuel economy is accounted for by the horsepower. And that's it for today. So, some essential questions. How does a linear equation summarize the relationship between two variables? How is the best linear model for a set of data determined? And why is it important to evaluate the residuals of a linear model?